Hello everybody, this is the second video of chapter 6 of the statistical learning course. So in this part of the chapter, we're going to see how to train decision tree models for classification problems. So many ideas introduced in the regression framework are applicable in the classification setting. Okay, so the idea to build up trees by recursive binary splitting and like stopping criteria or pruning trees still applies here, but there are slight differences in the training approach for a classification method. So the main difference is that the objective function which we consider when we make splits is different than for regression. So for regression, we considered um, the sum of squared errors, which had to be reduced when we make a given split. But when we work in a classification setting, squared errors doesn't make sense if the response is a qualitative class. So instead of using the sum of squared errors, we're going to use alternative metrics that we will discuss next. So uh, first, uh, before discussing these metrics, there's another difference that we've discussed a bit in the previous video, which is that when we divide the predictor space into various subregions, then to form a prediction in one subregion in a classification setting, we cannot average responses because responses are qualitative. So the typical way to make a prediction for a given subregion is to take the class of which is the most prevalent in the region and use this class to predict the class of all new observations falling in this region. So this idea of taking the most prevalent class would entail minimizing the error rate in the training set. So if we want to minimize the error rate, it makes sense to take the most prevalent class. Alternatively, if we want to consider asymmetry with respect to the various types of misclassification, another possibility would be to consider some loss function as we introduced in chapter 5. Okay, so instead of minimizing the error rate, we might minimize the expected or average loss or average cost of misclassification within a region to come up with a prediction. Okay, so again, either we can minimize the error rate or we could, by uh, picking as prediction the most prevalent class, or we could pick the class which minimizes the average cost within that region. Okay, so as we mentioned, the recursive binary splitting can also be used for classification trees, but as we said, there some of squared errors cannot be used as an objective function to be optimized when we make the split. We need to come up with something else. So once again, we could consider the classification error rate as a metric to be minimized when we make a split. Okay, so for example, if we have a region which we'd like to split into two, well, we could find the predictor among the set of predictors and the now it's not a threshold, but decide either which predictor and oh yeah, it can be a threshold. Okay, so here recall the response is qualitative, but the predictors can be quantitative. Okay, so we can find which predictor and which is the threshold we're going to use to make our segmentation so as to minimize the error rate in the combined two subsections of the original region. Okay, what quick note here, we're going to discuss it again. Here are the examples with the cutoff point. I'm going to assume that the predictors are quantitative, but the decision trees can work really well with qualitative observations. So instead of using a cutoff if, for example, the predictor is blue or orange or yellow, well, we could try to assign various combinations to one region and others to another. So maybe subregion 1 could be orange and the other could be all other colors. So yellow and I forgot the color, blue, I think I said. So we can, if the predictors are qualitative, we can still make a split by putting all the values on one side, well, some values on one side and all other values on the other side. Okay, but for the sake of simplicity, for the rest of this chapter, I'll presume the predictors are quantitative. Okay, so if we use the classification error rate as the metric to be minimized, uh, what would happen here is when we assign a prediction to a given region, the error rate in that region would be as follows. It would be 1 minus the maximum across all classes of the estimated probability of being in this class for the subregion R. Okay, so if in a given region R, let's give an example. We have three possible classes, so 1, 2, 3, and the proportions of observations in the three classes is 0.7, so 70% for first class, 20% for the third class, and 10% for the third, 0.7 for first class, 0.2 for the second, and 0.1 for the third class. So if we do that, then we definitely classify the observations in this region R as first class because it's the most prevalent class. So by classifying observations as first class, then we would have a misclassification rate of 30%, which is 10% plus 20%. So if we classify all these as first class, then the 30% which aren't in the first class are misclassified. So we see here that this can be expressed as follows. So the error rate is 1 minus the maximal probability across the various classes. Okay, so if we use the error rate to try to make the best split, what we would like to do is to choose a predictor xj and choose a cutoff point for that predictor where cutting with respect to this predictor and this threshold would yield the highest reduction in the classification error rate combined between the two subregions. This makes a lot of sense, but in practice, people who have trained these models have observed that sometimes there are other metrics that could be considered instead of the error rate, which could lead to decision trees with more interpretability, a better interpretability. Okay, so we will study these alternative metrics, which aren't the error rate, and which can lead sometimes to better or more interpretable decision trees. So these two metrics are known as the Gini index and the entropy. Okay, so if we have a subregion R of the total predictor space, then the Gini index associated with this all observations of this subregion R is defined as follows. So Gini index, so G stands for Gini index, R stands for subregion R. So GR is the sum across all classes of the estimated probability. So this is basically the proportion of observations from class G in that subregion R times 1 minus that probability. Okay, so basically these can so for a given small g, this corresponds to the variance of a Bernoulli random variable, which is worth 1 if g if you're in class G and 0 otherwise, and then you would sum all these variances across all possible classes. Okay, so we can understand this Gini index as some form of total variance across all classes. Okay, so we could understand the Gini index as some form of variability of the class among the subregion. So it can be shown that the Gini index will take very small values if all the p hats are either all very close to 1 or 0. Okay, so what we mean by all close to 1 or 0 is we mean almost all observations within that subregion have exactly the same class. So the Gini index is a way to measure, or a metric which allows measuring node purity or homogeneity of responses among a given region. Okay, so if for a given subregion of the predictor space R, all observations are, or almost all observations are orange and none are blue, then the Gini index will be close to 0. If there's a, like, let's say 40%, 60% or 50-50 split between blue and orange, the region is not very homogeneous because there's a mix of classes. So then the Gini index would be higher. Okay, so small values for the Gini index indicate that this node contains predominantly observations from a single class. An alternative to the Gini index, which is used in practice, is called the entropy. And the entropy for a given subregion R is defined as follows. It's minus the sum across all classes of still. So this is the same PRG. So it's the proportion in subregion R of observations falling in class G. And here we have the log of P. So here in Gini, this log was 1 minus P, and we didn't have the minus sign here, okay? But the formula looks a bit the same. And here we have this indicator here, just to mean that if the P is 0, then the log, we just set it to 0. Okay, we don't set this to minus infinity. So here, if P is equal to 0, then the log P is presumed to be 0. Okay, so this is what we said. Log P times the indicator if P is different than 0 means log P if P is different than 0, or 0 otherwise if P is equal to 0. The rationale for this equation is the following. So it's possible to show that when x tends to 0, x log of x converges to 0. Okay, so having this limit of 0 makes sense. And if you want to do that, please try it. You have to use l'hospital rule, or in French, la règle de l'hôpital, to solve this limit. Okay, so now what are possible values for the entropy metric? So since all these p's, they are between 0 and 1, because the p's are estimated probabilities of being in each class, which are between 0 and 1. So if we do that, log of p is between minus infinity and 0, and we multiply by something between 0 and 1. So this is between minus infinity and 0, and we multiply by a minus sign. So this whole something is between 0 and plus infinity. Okay, which means that we sum terms between 0 and plus infinity. So the total entropy has a measure or a value between 0 and plus infinity. So entropy is a quantity which is often discussed, for example, in physics. So in physics, the entropy has an interpretation as the amount of disorder. And this interpretation makes some sense here, because if for a given, it's the same thing that happens for the entropy. If the class for a given region is pretty homogeneous, so all observations are within the same class, then the entropy would be very close to 0. And conversely, if you have a lot of heterogeneity, so observations are from different classes, then the entropy would be large, so there's a lot of disorder among responses within the class. Okay, so this is just repeating what I just said. So it can be shown that the entropy will take a value near 0 if all the p hats are either close to 1 or 0, meaning that For one class, almost all observations are from that class, and for all other class, there's almost no observation from these other classes. Okay, so in a nutshell, like the Gini index, the entropy is small if the rth region, subregion, or rth node of the tree is very pure. And by pure, we mean homogeneous in the sense that all observations in the node have roughly the same class. Now, in terms of comparing outputs of the Gini index and entropy, well, often numerically they're pretty similar, and it's possible to show that if we use a Taylor expansion centered in 1, log of x can be approximated by minus 1 minus x. Okay, so here, if we replace, well, let's go back one slide. If we replace the log here by minus 1 minus x, we fall back on this Gini here where the log is replaced by 1 minus x and the minus disappears here. Okay, so this is why in practice using the Gini index and the entropy, sometimes it can give very similar results because both are very close to one another based on this Taylor expansion. Okay, so when we make a split, we have one region and we want to split it into two subregions. We need to try to make the split which minimizes either the Gini index or the entropy, but now we have to aggregate the entropy between the two subregions. Okay, so we want to minimize the total entropy across all the two subregions. Okay, so how are we going to do that? How can we aggregate the Gini index or the entropy across two subregions to come up with a total entropy in the region? So we shall do it according to the formula which follows. So if we have a subregion R, which we divide into two subregions R1 and R2, the aggregate entropy, so here I say entropy, but the same applies for the Gini coefficient, the aggregate entropy across the two subregions can be simply obtained by the following weighted the weighted entropy across two regions. Okay, so the total entropy for subregion R, if R is split into subregion R1 and subregion R2, then the aggregate entropy is simply pi 1 times the entropy of subregion R plus pi 2 times the entropy of subregion 2, where pi Rj, the weight for region Rj, is simply the number of observations in region Rj divided by the number of observations in total. So in region Rj plus in region J1 plus in region Rj2. So it's simply the sum of all total number, of all observations in the entire subregion R. So here are these two weights, pi 1 and pi 2, clearly sum to 1. So we can see that the aggregate entropy here, based on this formula, is a weighted value of entropies in all subregions, where the weights are simply the proportion of observations falling into each of the two subregions. Okay, so when we use either entropy or the Gini index to make a split within recursive binary splitting, we select a predictor and a cutoff for which the aggregate entropy across these two subregions is reduced as much as possible, and reducing the entropy would lead to nodes that are as pure as possible, so as homogeneous as possible, which we want. Okay, so we like to come up with nodes where the final result is, in this node all observations are of this class, in this other node all observations are mainly from this other class. So this makes sense. So now classification error versus entropy. It has been observed that the Gini index and the entropy are typically much more sensitive to homogeneity or node purity than is the classification error rate. Okay, so for this region, using entropy or the Gini index tend to lead to decision trees for which the nodes are much more homogeneous. And this is desirable in terms of interpretation. So if we have very homogeneous nodes, then the results of the decision tree can be very well interpreted, and this can be very accurate. Also, if we have a lot of homogeneity, because you have a high certainty in your predictions. So typically, the approach that is used in practice is when the tree is built. So to build the original tree T0, very large T, either the Gini index or the entropy are used for recursive binary splitting. And then once you have a very large tree, if you want to apply pruning to the tree through, for example, cost complexity pruning, you can still use Gini or entropy to prune the tree. And this would favor better interpretation because we said Gini index and entropy tend to favor homogeneity, which is might be clearer from the standpoint of interpretation. Conversely, for the pruning part, the error rate is often used in practice, and if your ultimate objective is to have a good error rate, then it might make sense to use error rate in the pruning. Okay, so when you build the tree, typically in practice, people use the Gini index or the entropy, but when you prune it, people use either Gini or entropy or the error rate. So it's more typical in practice to use the error rate within the pruning, but not when we build the original tree at the beginning. Okay, so one question we might have at this point is, why is purity important? Okay, so why don't we only care about accuracy in terms of error rates, and why do we consider homogeneity as important when we make some predictions? Okay, so to illustrate that concept, let's make a practical example which hopefully makes it more clear. Okay, so let's say we have a given node or a given region with 10 observations. 8 of them are within class 1 and 2 of them are within class 2. Okay, so for this big region, you would classify, of course, as class 1 if you want to minimize the error rate, and you'd say that you have an estimated probability of 80% of being class 1 and 20% class 2. So let's consider that you have a possible split which would give you the following outcome. So the outcome would be to split into two subregions, where in subregion 1 you would have 5 class 1 observations, and in subregion 2 you would have 3 class 1 observations and the 2 class 2 observations. So if you would have that, then the predictions wouldn't change, because for all the 2 subregions, so let's say subregion 1, clearly you would classify as class 1, but for subregion 2, the class 1 is still more prevalent. So because of that, you would still classify observations from subregion 2 as class 1. So here, originally, you classify everybody as class 1, and after that split, you classify everybody as class 1. Okay, so you might think, well, it's useless to make these type of splits because it doesn't improve the accuracy. So the predictions here aren't impacted by such split. However, if we use the Gini index, for example, to decide on which splits are worthy or which aren't, then let's see what happens. Okay, so if we consider the original subregion, the total subregion, then its Gini index would be, so here for class 1, it's 0.2 times 0.8 because we have 20% observation class 2, 80% class 1. So it's 20 plus 20% times 80% plus 80% times 20%, which is 0.32. Okay, if we do that, then we can compare this to the aggregate Gini index across its 2 subregions. So here, if we consider the first subregion, its Gini index is 0 times 1 plus 1 times 0, which is 0. And the reason it's because in the subregion 1, 100% of observations were class 1. In class 2, the Gini index for the second subregion not class 2, but subregion 2, the Gini index is zero point 0.4 times 0 0.6 plus 0 0.6 times 0 0.4 because if we go back, we have 60% of observations in class 1 and 40% observations in class 2 for that second subregion. Okay, so if we calculate that, this is 0.48. And the weights here for G1 and G2 would be 50% because recall that the pi's we had earlier are simply within the aggregation are simply the proportion of observations in each subregion. So if we want to aggregate the entropy between these two subregions, we multiply these by 50% and add them so that the aggregate entropy becomes 0.24. So we see that although the split doesn't impact at all the predictions, the split does reduce the aggregate and Gini index. So we start, if we make no splits, there's a total Gini index of 32.32. But if we make the split, then the aggregate Gini index becomes 0.24. So we're able to reduce the aggregate Gini. And so if we use a Gini coefficient approach, we would indeed make that split, even though it doesn't changes predictions and doesn't change prediction errors. Okay, so if it doesn't change predictions, why is it worth it to do that? So it might still be worth it in some cases if you're interested about the uncertainty about your prediction. Okay, so when you make predictions, sometimes you want a point prediction, but sometimes you're interested in the reliability or the uncertainty about your prediction. And here, if we make that split, then this gives us very good information about the uncertainty, because if we go back here, we can see that if we're in the subregion 1, then we have very high certainty of being class 1, whereas if we're in the subregion 2, then we have very little certainty that you're really in class 1, because it seems that class 1, it's only marginally more likely than class 2. Okay, so if we care about uncertainty about from our predictions provided by the tree model, then having more purity or more homogeneity might make sense, because it would allow to identify subregions where you have more certainty and subregions where you have less. So considering node homogeneity can be very important if you're interested in that determining the certainty or uncertainty of your prediction. Okay, so now one thing we might discuss is how do tree models compare to the linear models we've introduced in previous chapters. Because in practice, when you have a regression problem, for example, you might consider regression models or maybe tree models. So can the two be related together? Is there a way to kind of perceive their relationships with them? Well, in a typical regression framework, we have the response being the linear combination of predictors plus epsilon. So we have, in fact, that your prediction is is beta 0 plus sum over j xi j beta j. Conversely, when you consider a regression tree, then the predictions have the following form. So the prediction for the ith observation is simply the sum across all possible leaves of the tree. So here, capital J represents the total number of leaves in the tree of Cj, which is the prediction in the jth leaf, times your the indicator function if your ith, the predictors of your ith observation are in the subregion J here, like this. Okay, so we can see that regression trees, we can often still express them as a linear model, but where the predictors in that linear model are transformations of the original predictor, And these transformations are simply indicators if the predictors fall in a given subregion among the various subregions obtained from recursive binary splitting. Okay, so there's a parallel between linear regression frameworks and regression trees, where regression trees, they can be seen as a linear model with uh, with a transformation of the original predictors based on indicator variables if the predictors fall into specific subregions. So we've seen these, we've now discussed this parallel, but a question we might ask ourselves in practice is which one is better? Is there uh, a better model among linear models versus decision trees? Well, there's no single answer for this question. Okay, so if you have a given problem where the relationship between the predictors and the response is pretty close to linear, then uh, linear models might work very well. Okay, so you will get low bias because the true relation is linear, and low variance because linear regressions are uh, models with very low variance. So if the relationship between predictors and the response is close to linear, then linear models will provide low variance and low bias, so very good predictions. Conversely, if the relationship between the response and the predictors is very complicated, very nonlinear, then decision trees might do better because the linear models will be very heavily biased. So if you have very complex relationship between predictors and the response, decision trees might do better. So there's no single best model. The best model really depends on your application and your given problem, and so each given problem have different shapes of patterns linking the predictors and the response. So depending on the shape of the pattern, you might favor either one or the other class of models. So what are advantages of decision trees? Well, as we've seen, decision trees are quite easy to interpret and explain. Okay, so if you have a decision trees like the hitters example we had at the beginning of the previous lecture, well, it's very easy if you're in a meeting and you want to explain how you come up with your prediction. Okay, you check the number of years, and if the number of years is bigger than that, you check the number of hits, and then this is your prediction. Very easy to interpret, and they have a very nice graphical representation. It's also believed by some people that decision trees closely mirror uh, human decision making patterns. Okay, so when we make decisions with predictors, we don't mentally calculate necessarily like polynomial regression or something like that. We have thinking patterns which are a bit analogous to decision trees. So if we like to just mentally assign a value for the response, we might think about the most important predictor, check its value. If it's low, then maybe check other more minor predictors, adjust a bit, and then come up with predictions. Okay, so for that reason, people think that decision trees closely mirror human decision making. So uh, it helps interpreting the results. Finally, decision trees can easily handle qualitative predictors without creating dummy variables. Okay, so if we want to apply a linear regression and there's qualitative qualitative predictors, then we would need to create new quantitative random variables, which are of the following form. So first, an indicator if you're in class 1, second, an indicator if the predictor is in class 2, etc. So you need to create many dummy variables to use qualitative predictors in the regression setting, whereas decision trees, it's very easy to cope with qualitative predictors. So if you make a split, for example, you can say, I'm going to put a, a subset of the classes in the values of the qualitative predictor into one subregion, all the other values into the other subregions, and it's really not a problem. Okay, so these were advantages. Now disadvantages. Sorry, I can't pronounce that. Like what aren't advantages is the following. So, as we said, for standalone decision trees, they typically don't have the same level of predictive accuracy as some of the other regression methods discussed earlier. Okay, so if you want very precise predictions, then standalone trees might not work very well. And moreover, trees can exhibit sometimes high variability of predictions and can be non-robust in the sense that a small change in the data can cause a very large change in the final estimated tree. Okay, so maybe if you change a few variables, the value of few variables, then maybe the early split would completely change. And if you change the early split, then all subsequent splits will also change. So it might dramatically impact your decision tree. So we can see that trees can be very sensitive to changes of value of observations and can be non-robust. So the idea, what's going to follow in this chapter is we're going to, instead of using a single tree, we might use multiple trees to make the prediction based on a single data set, and then by aggregating the decisions provided by these many trees, hopefully it's going to stabilize predictions and lead to less variability. And by stabilizing predictions, we would have less prediction variance and hopefully higher predictive performance out of sample. So we will finish this here and discuss these methods for tree aggregation in the subsequent lecture. So thank you and have a nice day.